Greetings everyone. Our capstone project title is Flying Ad Hoc Networks Routing Protocols.
A comprehensive study of metrics and challenges.
Our team consists of myself DHIVYA
and myself Kishore, and our guides are Jeremy sir and Pradeep Kumar sir.
So what is FANET? FANET stands for Flying Ad Hoc Network, which is a type of network that consists of a group of small UAVs connected in ad hoc manner, which are integrated together to form a team to achieve high-level goals. While both MANET and VANET have their own unique strengths and applications, there are certain scenarios where neither of them is ideal. For example, in a disaster response scenario where both vehicle and person are involved, a combination of MANET and VANET technologies may be required to provide reliable communication and coordination. This is where FANET, that is Flying Ad Hoc Network, comes into picture. FANET is a type of ad hoc network that is designed specifically for unmanned aerial vehicles, UAVs, to communicate with each other and with ground-based infrastructures. FANETs have a range of potential applications including disaster response, border surveillance, and environmental monitoring. When compared with VANET shows an upper hand in reliability, adaptability, flexibility, and there are a bunch of applications we can see over here in which FANET stands in a superior position than MANET and VANET. So there's more mobility, node speed, infrastructure, implementation of network. Potential application of FANET are limitless, as we can see from the examples listed on this slide. Irrigation purpose in agriculture, military operations, rescue operations, journalism and news, infrastructure, wind estimation, managing wildlife, etc. So the beauty of all these applications is the performance metrics required to satisfy all these applications aren't the same. Each and every application requires a different performance metrics that needs to be satisfied. For example, for irrigation purpose in agriculture, battery life is very important because for irrigation purpose, if the drone has to go all around the area, the battery life should be proper for that. And then for military operations, delay will not be tolerated. For rescue operation also, the delay will not be tolerated. And then for forest fire detection, same delay. And then for infrastructure development, PDR and throughput is very important, and I can just go on and on and on. One of the key applications is forest fire detection, which we have illustrated with a set of drones flying over a forest. Each drone is equipped with a camera that can transmit live feed to a ground-based station via Wi-Fi or radio frequency. In the event of fire, the ground station can quickly direct rescue teams to the affected area based on the information received by the drones. To illustrate FANET in search and rescue scenario, consider the example of a house in a fire where firefighters need to rescue people and extinguish the flames. In this scenario, the firefighters can deploy drones to fly over the affected area and provide a comprehensive view of the situation. This enables the firefighters to respond quickly and take appropriate actions to save lives and properties. Here we can see the firefighters having a comprehensive view of the whole situation before they could decide what is their next move. So next is disaster response. In this disaster response scenario, you can see that the bunch of rescue people, they come and they place the drones all over the place, and the drones fly all around the area. They are having a mission and path planning procedure going on, and then here they are doing the path planning. You can see the path planning over here, and then here the aerial surveillance is going on. So the people who are away from the affected area, they can see what is happening, where they need to move the drone to rescue people. So with the drone's location, they are able to locate the people, so the victim is being located. So you can see two types of situations in which the drones are helping over here. A, they will go and help the people in need. So here if you see, they'll be sending the people, which you'll be seeing in the next clip. So the email is being processed to see who the person is. So here they are going and they are trying to rescue the person who has been affected. So they are getting the video, which the image processed through a wireless device, and they are rescuing him. And then in the next clip, you will be seeing a drone delivering a first aid kit to the affected person. So yeah. And then another application where drone can be used is agriculture, and one such important application in agriculture is aerial spraying. These drones can be used to spray water and other pesticides on the crop. throughout the field. These drones can act fully autonomous, and the important thing about them is that they have the ability to know when they need charge and when they need the liquid load to be filled again.
FANET's routing protocols play a crucial role in ensuring efficient and reliable communication between nodes. So FANET routing protocols has three types: proactive routing, which has OLSR, reactive routing, which is AODV, and hybrid routing, which is ZRP. So, first of all, we'll see proactive routing. Proactive routing protocols such as OLSR, which is Optimized Link State Routing Protocol, work by constantly maintaining and updating routing tables with information about the entire network. This allows for faster and more efficient routing decisions, but can also lead to high overhead and energy consumption. So, and next off we have AODV, which is reactive routing. So, reactive routing such as AODV, which is AdHoc on-demand distance vector routing protocol, works by discovering routes only when they are needed. This reduces overhead and the energy consumption also be reduced, but can lead to slower routing decisions, especially in highly dynamic networks. And next up we have hybrid. So hybrid, under hybrid, that is ZRP, zone routing protocol, combines the best of both, which is proactive and reactive. The ZRP divides the network into zones like zone 1 and zone 2, and uses proactive routing within each zone. So if there is routing anyway required under one zone, it uses proactive, and if the radius is away from the zone, it goes to reactive. This allows efficient routing decisions with reduced overhead and also energy consumption. So in general, the choice of routing protocol depends upon specific requirements in FANET. Proactive protocols like OLSR are suitable for networks with low mobility and high communication requirements, whereas reactive protocols such as AODV are better suited for highly dynamic networks with lower communication requirements. And hybrid protocols like ZRP offer balance between proactive and reactive protocols and can be useful for networks with varying mobility and communication requirements. Apart from the traditional routing protocols, there is also a concept called clustering in FANETs, which has static and dynamic clustering types to work on with. Clustering is a significant concept in FANETs as it helps to improve the network efficiency scalability by dividing the network into smaller groups or clusters. One popular clustering protocol in FANET is called LEACH, which is Low Energy Adaptive Clustering Hierarchy. LEACH dynamically forms clusters and assigns nodes as cluster heads based on their energy levels, and thus reduces the overall energy consumption in the network. So this is an example of clustering in FANET, and another clustering technique that is gaining popularity is the dynamic clustering using K-means algorithm. This technique dynamically forms clusters based on the spatial proximity of nodes and is useful for FANETs with higher mobility. The K-means algorithm clusters nodes based on their distance from each other and dynamically adjusts the cluster formation as the nodes move. This allows for more efficient resource utilization and improved network performance. In general, clustering is a significant concept in FANETs as it helps to improve the network efficiency, scalability, and reduce energy consumption. LEACH and dynamic clustering using K-means algorithm are popular clustering techniques that can be used to optimize the performance of FANETs.
The software which we have used to implement our FANET scenario is called NetSim. It's basically a network simulator. So you can see the layout. There are 4 UAVs in this scenario, and it is connected using an AdHoc link, which is basically a wireless link. So here in AdHoc link, we have made our changes for the channel characteristics. The software which we use for designing our FANET scenario is called NetSim, which is basically a network simulator. Here in the layout, you can see there are 4 UAVs that are connected to an AdHoc link, which is basically a wireless link, and all these UAVs are also wirelessly connected, and there is a voice communication going from UAV 1 to UAV 2, and there is another voice communication going between UAV 3 and UAV 4. So in the AdHoc link, you can basically model your channel characteristics. So here you can see the settings of channel characteristics which we have used are path loss only. So other options available here are no path loss, shadowing and fading, path loss and shadowing and fading. So, but we didn't go with the other three options because we kind of wanted to do a realistic scenario, and no path loss is the opposite of realistic scenario, because in realistic scenarios there will be at least little amount of path loss, and path loss shadowing, fading and path loss shadowing are very much realistic in nature, but because of their probabilistic nature, it is not really suitable for analysis purposes. Therefore, we have went with a deterministic model called as path loss only. The path loss model which we have modeled over here is a range-based model. So the range which we have set here is 250 meters, which we took from a reference research paper. So it basically means till 250 meters the communication will happen without any problem, and after 250 meters the communication will not happen. And the propagation medium is of course air. Other than channel characteristics, mobility model plays an important role in FANETs. Integrating mobility model in FANET is crucial because these networks are designed to be operated in dynamic and mobile environments. Mobility model helps to simulate the movement patterns of nodes in the network, which is essential for evaluating the network's performance in different scenarios. By integrating mobility model in FANETs, researchers can be better understand how node will move and interact with each other in different environments and optimize the network's performance accordingly. Other than channel characteristics, the another important parameter which we need to model for a scenario is mobility model. Integrating mobility model in FANET is crucial because these networks are designed to operate in dynamic and mobile environments. Mobility models help to simulate the movement patterns of nodes in the network, which is essential for evaluating network's performance in different scenarios. By integrating mobility model in FANETs, researchers can better understand how nodes will move and interact with each other in different environments and optimize their network's performance accordingly. This is important for testing and evaluating new protocols and algorithms and improving the overall efficiency and effectiveness of FANETs. So here you can see we have used the mobility model we have used is a random waypoint with a velocity of 10 meter per second and a pause time of 1 second. So a random waypoint is one of the popular mobility models used in FANET. It assumes that nodes move randomly throughout the network with a specified maximum speed, which is 10 in our case, and the pause time, which is 1 in 1 second, as I mentioned before. This model is useful for simulating the movement of nodes in scenario where there is no specific destination or pattern to their movement. By using the random waypoint mobility model in FANET simulations, researchers can evaluate the network's performance under realistic and dynamic conditions. This can help to identify potential issues and optimize the network's performance for real-world deployment, which is exactly what we are trying to do.
Now I will demonstrate a 3D simulation by combining NetSim and MATLAB, since the NetSim lacks the support for 3D simulations. Why I am doing this is because all these demonstrations which we are given are in 2D, but the calculations done behind are actually 3D calculations, which I will be demonstrating you right now. So this is how the background calculation goes on. So since we are given 4 UAVs, there are 4 UAV graphs given here, all representing in 3D. So x-axis, y-axis, z-axis, and the black part is the trajectory. Trajectory is from the start of the run until the end, where does the path is being gone, where the path is being gone, and how much distance it has traveled. So background the MATLAB calculations are going on, which is the interface with MATLAB, and in this front we have the 4 graphs which represent the 4 UAVs in 3D. My teammate and I simulated for 5, 10, 15, 25 and 50 nodes using the routing protocol, mobility model and channel characteristics mentioned before. We then assess the result using metrics such as the packet delivery ratio, average delay, throughput and energy efficiency. Based on the analysis, we link the routing protocol that met a specific application requirements
of 25 nodes with constant bitrate traffic from node 1 to node 19 with AODV protocol and random waypoint mobility model. Here I'll show you how the mobility model, the packet transfer is visualized and how the results are obtained. So first we'll run this configuration file. We are setting the simulation time to be 100 seconds and we are recording the animation. So after the simulation is being run, we get these graphs, which is the plot, the simulation results and the animation file. So in this GUI, we can see the packet transfer and the nodes mobility. And in this GUI, this is the result column where the packet generated, packet received, all the simulation parameters and the QoS metrics can be measured, and the results will be given here. We will be recording all the results from here. And we also have the print result and the open packet trace, which helps us to identify any root causes for the issues which may arise in the future. And also we can find the root causes where the Excel will be generated for each simulation which we do.
So now we are going to discuss our results. Here we have used two types of traffic applications. One is CBR traffic, it's constant bitrate, and another one is video traffic. So the first graph is PDR, which is number of nodes for CBR traffic. So here in the graph, if you can see, if the number of nodes in the network is small, the network's connectivity deteriorates, destabilizing it and ultimately lowering the PDR. Conversely, as more nodes join the network, the probability of successful delivery of packets by AODV increases since more nodes are available to forward the packets. However, if the network becomes denser, the PDR of AODV declines due to increased contention interference, leading to more packet losses and collisions. Furthermore, the higher network density could cause greater route maintenance overhead, which may further reduce the PDR. In contrast, OLSR routing protocol is proactive in nature. It continuously maintains and updates network topology information to facilitate efficient routing. Its performance declines as the number of nodes increases due to network contention. So next, similarly, if you see, ZRP operates in a reactive mode when the destination node is beyond the zone radius, leading to performance similarity to AODV. So next, if you see, the next graph is throughput versus number of nodes for CBR traffic. So based on the results in the given figure, AODV appears to have relatively higher throughput compared to OLSR and ZRP. It is likely due to AODV's reactive routing approach, which only creates routes when it's needed, resulting in lower overhead. As the network density increases, AODV's connectivity also increases, leading to improved throughput as more nodes become available for forwarding. In contrast, OLSR and ZRP use proactive and hybrid routing technique respectively, and as network density increases, contention lower throughput compared to AODV. So next we are going to see delay versus number of nodes for CBR traffic. In the above figure, similarly, the application delay for AODV is relatively higher compared to OLSR and ZRP, and it is because if the topology changes, it's because of the topology changes, AODV has to search for a new route and takes time compared to OLSR and ZRP, which constantly updates the routing table. Note that the delay for 10 nodes is higher for AODV and ZRP compared to 5 and 15 nodes is because of the random movement of the random waypoint, which is the mobility model which we are using, of course. And the last graph for CBR traffic is energy consumption, which is number of nodes. According to the given graph, the proactive routing protocol OLSR consumes more energy than the reactive AODV and hybrid ZRP. This is because proactive protocol exchanges control messages continuously even when there is no data to transmit, resulting in higher overhead and energy consumption. In contrast, reactive protocols exchange control packets only when a data packet needs to be forwarded, resulting in lower overhead and energy consumption. Hybrid protocols exchange control messages within their zone to maintain network topology information, resulting in moderate level of overhead and energy consumption. So that's all for CBR traffic. Now we'll see for video traffic. So video traffic, also the first graph we're going to see is PDR versus number of nodes. In this architecture, this ZRP architecture facilitates swift adaptation to change in network topologies, leading to enhanced PDR. So that's the reason why ZRP shows relatively better results than the other two routing protocols. And the next graph we are going to see is throughput versus number of nodes of video traffic. ZRP's hybrid design is capable of mitigating control overhead and by partitioning the network into zones. In each zone, a proactive routing protocol is utilized, while reactive routing protocol is utilized for interzone communication. This is utilized for interzone communication, as I said before. This method can lessen the control overhead in the network, leading to a superior throughput video traffic, which relies on the proficient utilization of accessible bandwidth. So that's why ZRP outperforms AODV and OLSR in video traffic for throughput. And the next graph is the delay graph for AODV, OLSR, and ZRP for video traffic. The application delay for AODV is relatively low when compared to OLSR and ZRPs, because even if the topology changes, AODV has the capacity to transmit data with higher PDR, but for OLSR, the delay to transmit video traffic is higher due to the overflow of control packets from each node, and the data packets sent by the video traffic is much higher than the CBR traffic. ZRP, on the contrary, has balanced the performance metrics as it uses a hybrid approach which efficiently transmits the video traffic packets. Note that the delay for 15 nodes is very high for AODV, OLSR, and ZRP because of the random movement of the nodes, and RWP, which is the random waypoint, which is the mobility model which we are using, and with small increase in the network density will affect the delay of the network due to video traffic's large number of data packets sent. So the last graph which we are going to see now is energy consumption. So from the graph, not this one. Yeah. So from the graph, which we can see that the ZRP uses a hybrid routing approach which can reduce the amount of energy consumed by routing discovery and maintenance by dividing the network into zones, each using a proactive routing protocol and interzone routing protocols, a reactive protocol. ZRP can minimize energy consumption while maintaining efficient routes. So now my teammate Ramkishore will explain you about the hybrid routing protocols, which we have hybrid WSN routing protocols clustering.
So for in this graph which we are about to see is energy consumption versus number of nodes for leech. So leech is a static clustering protocol where according to the graph we can see the trend at which the average energy, minimum energy, and the maximum energy consumed by a sensor node reduces as the number of nodes increases. It can be inferred that with the increase in the number of sensor nodes, the number of nodes under a cluster head increases, and since the cluster heads are assigned with keeping them as the centroid of the cluster, and hence calculating the energy consumed by energy consumed. By using leech, the energy utilized by each node and the average energy consumed is reduced, hence increasing the lifetime of the network. This type of static clustering can be implemented in applications which require short area to cover and get sensory data for a long period of time in repetitive intervals. So next we have dynamic clustering. For dynamic clustering, in this graph you can see that it is observed that using the k-means algorithm to find the centroid of the network among the clusters and finding which node has more energy in the reserve compared to the others is elected as the cluster head. When observed for 16, 36, and 64, the minimum energy consumed by the node, the maximum energy consumed, and the average energy consumed by the node are similar for each cluster. This indicates that using dynamic clustering can improve the survivability of the network and hence extend its lifetime. So to conclude, according to the aforementioned results which we got, it can be inferred that for applications prioritizing PDR and throughput, such as the environmental data collection and precision agriculture, traffic congestion management, AODV is relatively better suitable routing protocol. Conversely, for delay-sensitive applications like search and rescue missions, disaster response, military surveillance, OLSR is a relatively better option. Finally, for the energy-efficient applications, which includes the wildlife monitoring, forest fire detection, maritime surveillance, there's a zone routing protocol. ZRP stands out as the optimal solution in situations where the network density comprises fewer than 50 nodes. However, when the number of nodes within the network exceeds 50, particularly in case of sensory data collection applications, the utilization of static clustering techniques such as leech and dynamic clustering techniques such as using the k-means would be more fitting alternative. In cases where all the aforementioned factors are equally important, we find that we conclude that AODV is the optimal choice as it exhibits superior overall comparison of effectiveness with the remaining two protocols evaluated in this study.